New pictures obtained by the James Webb Space Telescope have stunned researchers as opposed to growing our perception of the universe. These pictures revealed a disturbing reality. Our ongoing comprehension is lacking to get a handle on the possibility of the universe in its starting stages, where the hypothesis of the universe's starting point appears at its limits. This propels us to ponder new hypotheses about its beginning stage. The question arises as to how the universe was formed comprehensively and why this new revelation challenges even the most experienced space specialists to sort out more about the Big Bang and the ever-evolving nuances of the discovery. We ought to assess the possibility of the Big Bang itself instead of popular thinking. The Big Bang was not an impact in prior space, rather it was space itself that started around 13.8 billion years ago alongside matter and time. From a remarkable characteristic in actual science and cosmology, a cup describes where gravity is so remarkable that the curvature space-time becomes infinite. Today, following billions of years since the beginning of the universe, we see that our celestial home is part of a significant cooperation for experts. This addresses an essential part of the universe since its very existence. Its ceaseless development is important to understand. The universe isn't wandering into prior space, rather space itself is persistently growing in size as indicated by conventional theories. The first stars began to shine somewhere between 200 and 300 million years later, the Big Bang marking the end of the so-called Dark Age. This was when the first radiant heavenly objects clustered together to form mature galaxies. However, how quickly these worlds developed remains an ongoing mystery. A huge piece of data emerged through the first pictures caught by the James Webb Space Telescope in July 2022. Experts announced that the telescope had detected various galaxies, some of which had existed around 300 million years after the formation of the universe. However, compared to the celestial structures that formed billions of years later, these early galaxies were considerably smaller and less massive. This fits perfectly with the scientific model accepted by experts. The density of matter in the young universe was simply not enough to lead to galaxies the size of those observed today. This began as the discovery of 6 amazing redshifted radiant spots from James Webb, which ended up triggering one of the most significant astronomical crises of recent times. Although these newly discovered galaxies are similar in age to previously recorded worlds, they are nearly as massive as our own Milky Way galaxy. This has created an intriguing mystery in cosmic cosmology. After examining a series of pictures caught by the near-infrared camera, experts identified the aforementioned light sources using redshift. Specialists confirmed that the light from these objects took more than 1 billion years to reach our eyes on Earth. As a result, we are dealing with structures that had already existed somewhere between 570 and 700 million years after the confirmed Big Bang. By looking at the attributes of these designs, it was concluded that the Webb telescope had captured 6 early galaxies in the image. Surprisingly, these galaxies were so enormous that they defied conventional cosmological assumptions. Instead of finding the expected dwarf galaxies, structures were identified that were almost as large as our own Milky Way galaxy, despite having formed early in the universe's history. If we continue to analyze the data gathered by the James Webb Telescope, this gravitationally bound collection of stars was already more than 10 billion times the mass of the Sun at that time, with one possibly unbelievable 10 billion solar mass mark. However, whether this possibility is considered, the mystery isn't fully settled. Even in this scenario, there would be much more vast mass in the early universe than previously anticipated, introducing a riddle. The identified objects suppose virtually all conventional cosmological theories. Even if only one of these galaxies turns out to be real, it would challenge our past assumptions to make sense of the existence of these designs. In addition, the density of matter in the early universe would have to be several times greater than previously accepted to explain this phenomenon. Another similarly bizarre explanation depends on the possibility that these galaxies formed in a way that is still completely unknown to us. These discoveries and the discussions they are raising will lead to further examination of the Big Bang Theory. Many space experts with alternative views are frustrated, and their perspectives are often heard in scientific journals. Even those who express doubts about existing hypotheses are frequently labeled as inappropriate or peculiar. However, it is clear that even experts who still defend the Big Bang Theory are continually confronted with questions without answers. These inquiries include specific issues such as why and how 13.8 billion years ago something literally rose out of nothing. Could something really start from nothing, or was there some triggering event, or was it all a mishap? Stephen Selling pointed out that the nature of time as we know it began with the Big Bang. Therefore, this process could not have been set off by something else or by an external cause. A similar ambiguous question relates to the consistency of radiation and density throughout the universe, regardless of which direction or at what distance we look on a larger cosmic scale. We find similar densities and distributions of galaxies, nebulae, and radiation across the universe. Modern theorists explain this phenomenon by the theory of cosmic inflation. However, various experts extend this assumption further with a theory of turbulent inflation. According to this idea, inflation has only halted in certain regions like bubbles and continues incomprehensibly elsewhere. This suggests that multiple universes could form in these bubbles, each with its own unique physical laws. Within this model, a big question arises: what if the universe doesn't represent the total whole? And more imaginatively, what if another universe existed before our own? In this case, the Big Bang would become part of a larger cycle. According to this perspective, our universe is part of a larger, more complex structure. Within this model, the possibility of an eternal pattern of collapse and resurrection of the universe is advanced. However, this is not the only viewpoint presented in the field of cosmology. Apart from the theory of how things came to be in 1955, for example, an article appeared in NASA's Big Time suggesting that there may have never been a Big Bang since the universe has existed for an indefinite period. In this view, the expansion of the universe would be non-existent, and the constant improvement of matter could give the impression of consistent development. Another interesting controversial theory comes from the domain of quantum physics and string theory. Some experiments have suggested that our universe and everything in it may be a projection or a higher dimensional simulation. While this could seem like the plot of an unconventional science fiction film, it could be linked to the Kesef scale, which measures the level of advancement of a civilization based on its ability to harness energy. If there were a Type 3 civilization capable of fully utilizing the power of an entire galaxy, it could have created a perfect simulation. However, determining the reality of such a situation is a deeply complex matter. Exploring the depths of cosmology and the origins of our universe leads us into a domain of profound mystery and ongoing scientific inquiry. The new pictures captured by the James Webb Space Telescope have reignited conversations about the very fabric of our reality, testing established hypotheses and prompting scientists to reconsider fundamental aspects of cosmological Understanding at the core of this inquiry lies the theory of the universe's origin, a cornerstone of modern cosmology. According to this theory, approximately 13.8 billion years ago, the universe emerged from an extraordinarily dense and hot state, expanding rapidly and resulting in the space-time and matter we know today. This colossal event was not simply an explosion within pre-existing space, but included the earliest inception of space itself, the notion of a singularity where gravitational forces are so intense that space-time curvature becomes infinite, supports our understanding of this early cosmic epoch. Yet the discovery of early galaxies by the James Webb Telescope challenges our assumptions about how rapidly structure formed in the universe's infancy. These galaxies, detected within a few hundred million years of the Big Bang, appear surprisingly developed and massive when compared to current cosmological models. One of the key questions raised by these revelations is the nature of cosmic inflation. According to the prevailing theory, inflation occurred within fractions of a second after the Big Bang, causing the universe to expand drastically. This rapid expansion would explain the uniformity of the cosmic microwave background radiation observed across the universe today. However, current discoveries suggest complications in the early universe's development that may require adjustments to inflationary models. The formation of galaxies like those observed by the James Webb Telescope forces cosmologists to rethink the conditions and processes that govern the universe's early history. These galaxies, now massive and large so soon after the Big Bang, suggest a density of matter that exceeds previous estimates. The mystery deepens when considering how such massive structures could form and evolve in such a short cosmic time. Additionally, the discovery of these early galaxies raises intriguing questions about the nature of dark matter and dark energy, two elusive components that make up most of the universe's mass and energy content. While dark matter is believed to provide the gravitational framework necessary for galaxy formation, the distribution and properties of dark matter in the early universe remain uncertain. In line with these astrophysical mysteries, theoretical physicists are exploring alternative cosmological models that challenge the standard Big Bang perspective. Some theories suggest that our universe is only one of many in a vast multiverse, each with its own unique physical laws and constants. These ideas, emerging from advancements in string theory and quantum cosmology, propose a more complex and interconnected universe than previously imagined. One theory gaining traction is eternal inflation, where universes constantly emerge from a larger inflating space. This theory suggests that our universe could be just one bubble among countless others, each with its own set of physical properties. The challenge lies in finding observable evidence to support such speculative ideas as they push the limits of observational validation. Another provocative theory posits that our universe exists within a simulated reality, much like a computer-generated recreation. This concept draws parallels to advancements in artificial intelligence and computational science, where simulations can mimic complex systems with remarkable fidelity. If true, our perception of reality as a distinct physical universe could be fundamentally altered, raising significant philosophical and scientific questions about the nature of existence. Furthermore, advancements in observational astronomy continue to reveal the vastness and complexity of the universe. Telescopes like the James Webb Space Telescope, with its remarkable sensitivity and resolution, promise to uncover even more secrets of the universe. Future observations may shed light on the earliest moments of the universe, offering clues to its ultimate fate, and the fundamental principles governing its evolution. Beyond observational astronomy particle, physicists are investigating the fundamental particles and forces that shape the universe. The quest to unify gravity with the other three fundamental forces, electromagnetism, the strong nuclear force, and the weak nuclear force remains a central goal of theoretical physics. Models like quantum gravity and string theory offer potential frameworks for understanding these key interactions at both the smallest and largest scales of the universe. In the realm of quantum mechanics, the nature of time itself remains a subject of intense debate. Quantum theories suggest that time may be evolving or even elusive at the fundamental level. Understanding the nature of time within the context of cosmological models could reshape our understanding of the universe's beginnings and evolution. Additionally, the search for extraterrestrial life continues to captivate the public imagination and drive scientific inquiry. The discovery of exoplanets, planets orbiting stars outside our solar system, has expanded our understanding of planetary diversity and the potential for habitable environments elsewhere in the universe. Future missions, such as the James Webb Space Telescope's investigation of exoplanet atmospheres, may provide evidence of biosignatures indicative of life beyond Earth. In addition to these scientific pursuits, cultural and philosophical reflection tie-ins on the universe enhance our understanding of our place within it. Questions about the meaning of existence, the possibility of intelligent life elsewhere, and humanity's future in space exploration drive research and debate across disciplines.